Welcome back to Physics 246 Online. Today I'm going to give a brief introduction to the remaining two probability distributions that are covered in Bevington and Robinson, Chapter 2. First, the Gaussian distribution, and finally, the Lorentzian distribution. This will just be a quick overview, so please consult the text for more details. So in Section 2.3, Bevington asks us to consider those cases that are very common in experimental work where the probability of success in a single trial is not small, and where n, the number of trials, is typically very large. And what's also helpful about this situation that we're going to use to define the Gaussian distribution function is we want to be able to handle cases where the number of successes is not just an integer value. And up till now, we've talked about counting experiments where we either have an event or we don't. We also have lots of situations when we do experiments and we're measuring quantities that aren't just successes or failures. They might be the physical value of a particular quantity, like a particle that's emitted from a radioactive nucleus. We might want to measure its energy. And there may even be some quantities that we measure where the value could be negative. So the binomial and the Poisson distribution functions will not handle those situations. So we'd like to know what probability distribution should we use to describe those cases. And the answer is the Gaussian probability function. And that's defined with this characteristic Gaussian term that is e to the minus a quantity squared. X, of course, is the value. Mu represents the mean of the parent distribution, and sigma represents the standard deviation. The coefficient out in front is defined in such a way so that if we integrate this probability distribution over all values of the quantity that we're measuring from negative infinity to infinity, we get 1. In other words, the Gaussian probability function with the appropriate factor out in front is normalized. And one way to simplify the mathematics just a little bit is to define a quantity z that's dimensionless, that is going to go into the exponent, where z represents, for a particular value x, how far it is away from the mean as a ratio of the standard deviation sigma. So if we do that with z, the functional form becomes a little bit simpler, and we end up with this dimensionless, with the dimensionless variable z involved, we have 1 over root 2 pi times e to the minus z squared over 2. And again, this has the nice property that if we integrate over all the values, now z represents what the outcome is of our experiment because it's related to the actual measurement x, but we integrate over all values of z and we get 1. So then the properties of the Gaussian probability function, it's continuous in x, whereas the Poisson and the binomial distribution functions, x was simply the number of events, and it was either, it was always an integer. X, in the case of the Gaussian distribution function, is defined so that it can be fractional. It can be decimal, any real value. Of course, it's normalized. The Gaussian mathematical form is remarkably easy to use, and there's some properties that it has. For example, when you multiply Gaussians, the product of two Gaussians is also a Gaussian, and that's very useful mathematically. It's also easy to use because it's easy to generate the values of PG. We don't have factorials to calculate, and that makes things quite a bit easier. Also, we can define a differential probability so that if we take a particular small range of x values and multiply by the probability function itself, that defines the probability of getting a particular measurement in that range of x values. So why is it appropriate to use the Gaussian function? Well, we can show, and rather than make a detailed analytical argument, we'll just plot the Poisson and the Gaussian probability functions together on a graph, but we can show that for large enough values of the mean, then the two functions become essentially indistinguishable. But an even more compelling reason to use the Gaussian distribution function is basically because it works. If we do lots and lots of measurements of a quantity where the only errors that are involved are random errors, basically we can just show that we can draw a Gaussian curve through the histogram that represents the collection of all those measurements. So it's really justified empirically, primarily because it works. Here, for example, is the plot of a Poisson and a Gaussian distribution function overlaid on top of each other for a mean value of 10. And you can see that there's a little bit of discrepancy in the tails and a bit of a shift here near the peak. But if this value x gets larger and larger and larger, if the mean value gets larger and larger and larger, then these two functions will become essentially indistinguishable. So we use the Gaussian function because it gives us basically the same shape as the Poisson function in the limit of large values of mu, and it's much easier to work with mathematically. Here, as I said before, we use a Gaussian function primarily because it works. Here are real data. These are a measure, like basically a histogram that shows the frequency, the number of counts of photons with particular energies plotted versus the energy. And then with the right parameters, you can see that a Gaussian function, which is the solid line, fits these data rather nicely. So once again, in real data situations where we've got random errors, the Gaussian function describes them well. We mentioned earlier that we can define this differential amount x, a certain range of x, and the area that's underneath that rectangle, if it goes up to the value of the probability function, tells us the differential probability of finding a measurement within that range. And it's often useful to not just do a calculation for one thin rectangle, but actually integrate over a range of x values. And that's a helpful thing to use to characterize the Gaussian distribution. And that's called doing an integrated area. So if there's n entries in our plot, the total area underneath a plot like the one on the previous slide should just be the total number of measurements, n. And we also want the integrated area under the Gaussian function to be n. So we know that the function itself, when we integrate it from negative infinity to infinity, gives us 1. So if we multiply both sides by n, then we can define a quantity here. The argument in this integral here is the quantity that when we actually integrate it, when we add up the values that we get from x equals negative infinity to infinity, we get n. And that's basically what a histogram is. A histogram is the display of the frequency of measurements that we obtain when we make repeated measurements, and it's defined for finite bin widths. So the predicted number of events at each bin, if the bin has a width delta x, would simply be this quantity n times the probability of getting a single event at that point multiplied by the bin width. So that would give us the number of measurements that we got within that bin. And of course, if we add up over all the possible outcomes that we can have, n here represents the value within that bin, how many different bins there are, we should once again get n. And so here is an illustration of that, where if we actually defined a range delta x and then found the area underneath the curve at that point over that range, we would get the total number of counts or the total number of measurements within that range. So, of course, with all of our probability distributions, we want to characterize them by the relevant central measures, the mean and the variance. And it's pretty obvious, although it's good to check it out, that if you evaluate the mean value or the expected value of x using the Gaussian probability function, indeed you get the mean. That's characteristic of distributions that are symmetrical like that. If you calculate the variance using the definition that we showed before, indeed you get sigma squared as the variance. So just because we threw sigma into the expression for the Gaussian function, that doesn't guarantee that it really is the standard deviation, but you can show that when you calculate the standard deviation the way we define it, you do get that parameter sigma squared for it. There's one other relevant parameter that we use to characterize the width of a probability distribution, and that's called the full width at half the maximum value. And gamma, the capital letter gamma, is used for that. And it's pretty intuitive. We'll show it on a graph on the next slide, but basically it's the width, it's the difference between two symmetrical values around the peak on the Gaussian function at which the probability is half of the maximum probability. So here, PG evaluated at x equals mu, that's the peak value of the distribution. Take that, multiply by 1/2, and we see that on either side of the mean, there's going to be a point where the probability goes down to 1/2. So when we show that graphically, here it is. The peak value is right around 400, so the half maximum value is right around 200. And if we look at the x values on either side of the peak, that full width at half maximum tells us something about how broad the distribution is for this particular measurement. It's called the full width at half max. It looks like it might be related to sigma, but it's actually a little bit more than 2 sigma. And so it's not quite the same thing as the standard deviation, but it is closely related to it, and it's a very nice intuitive value to use to characterize the distribution. So one last thing about Gaussian functions, we often want to find the integral underneath that for a finite range. And here's one definition. If you started at -infinity and integrate all the way up to x equals a, you could find the total area underneath the curve within that range. This area, of course, has to be less than or equal to 1, but you can't do this integral analytically. It has to be done numerically. So if you wanted to find what the integrated probability was between two values, two finite values, you would just take the difference of those two a values from -infinity to b minus the one from -infinity to a, and that would give you the integral in the range from a to b. And that's very useful in order to answer the question, what's the probability that I would get a measured value between a and b for a certain range? How do you do that integration? Well, you can either write your own program to do it, you can borrow someone else's program, or you can use a built-in Microsoft Excel function called normdist. And depending on what you put in for the final value within the parentheses of the normdist function, you can either put in 0 as the last value, and that will give you the probability of getting a measurement at a certain value of x, where the distribution is characterized by a mean and a standard deviation. And perhaps more usefully is when you plug in a 1 in that final place, that will give you the integrated probability up to that point. And so you can often use this normdist function to find the probability of getting a result in a particular range. So here is how you would do that, right? If you wanted to find out the integrated probability between mu minus sigma and mu plus sigma. So in other words, what's the probability of getting a measurement within one standard deviation from the mean? This is how you would set that up. And that normdist function would allow you to do that yourself using Excel. So just to show you what the results are when you do those kinds of calculations, you've probably seen these before in a previous class, but the integrated probability within 1 sigma on either side of the mean is 2/3, 66.7%. If you go out one more standard deviation, you get 95.4%. And so one useful consequence of this latter result is that in order to get a measurement that's more than 2 sigma away from the mean for a normal distribution like this, that would only happen in roughly 5% of all your measurements. And you could go out to 3 standard deviations and find out the probability of being that far away or further becomes very, very small. So results that fall that far away from the mean are very uncommon in a Gaussian distribution. And you can see on page 252 of your textbook that you can even come up with a plot of these a sub a values versus x, and you can define what's called the integral probability distribution. So just to summarize this introduction to the Gaussian function, it applies to continuous values of x. That's useful in a lot of experiments. It applies best when the value of n is large, which makes the mean large as well. We can evaluate it very easily knowing just the mean and the standard deviation, and it's a normalized probability function. So now, let's go on very quickly and move to the Lorentzian distribution function, the remaining one in Chapter 2. This one will be much shorter. It applies only in very, very specific cases. But it does help us in cases where we have physical phenomena that don't follow either the binomial, Poisson, or Gaussian. Well, what kinds of events are those? And one of them that's very common concerns resonant phenomena. This would it be examples where we're measuring the cross-section for a nuclear scattering event or nuclear reaction, or where absorption of radiation is involved. So you might have seen spectral plots with peaks representing either emission or absorption of radiation. And the shapes of those peaks are not the same as the binomial, Poisson, or Gaussian functions. They're actually something completely different. And you can predict what that is based on the solution to differential equations that govern those phenomena. So we have a name for that function. It's called the Lorentzian probability function. It's got a specific value here that is something that depends on this parameter gamma, where gamma over 2 represents the half width of this distribution. Gamma itself, as we'll see on the plot, represents the full width at half maximum value. So the probability of getting a result x relative to the mean of mu, where the distribution has this characteristic full width at half maximum gamma, is given by this function here. And if we integrate that over all possible values of x from negative infinity to positive infinity, we do find that the answer is 1. So it is a normalized probability distribution, which is helpful. And here's what you would do to evaluate that using, once again, a dimensionless variable z to simplify the mathematics. So the Lorentzian probability distribution function is similar to the Gaussian one in some ways. It's a continuous function of x, which is helpful for experiments where we're measuring a quantity that's not restricted to integer values. It's normalized. It's also symmetrical, as we'll see in just a minute, symmetrical about the mean. And we can write this differential quantity the same way that we did for the Gaussian function because it's a continuous function of x. However, here's the difference between the Lorentzian and the Gaussian function. The Lorentzian probability function has much more extended tails than the exponential tails of the Gaussian function. And we'll find out something interesting about the standard deviation of the Lorentzian distribution that makes it different from the Gaussian. So let's take a look at this spreadsheet plot where we plot together for a function that has a mean of 10, the Gaussian and the Lorentzian function. And you'll see the big difference is the Gaussian function is much sharper and overall narrower than the Lorentzian function, simply because it tails off to 0 much more rapidly. If we look at the Lorentzian function, right, it's got a lower peak and it's got these much longer tails. So the integral underneath both of these curves is the same, right? It's equal to 1. But much more of that distribution is spread out further away from the mean in the case of the Lorentzian function. And this just happens to turn out to be the way that experiments work when they are measured for phenomena that display this idea of resonance. All right, central measures. Let's look at the mean and standard deviation. Direct integration can verify, as you would expect for a symmetrical distribution function, that the mean value of x is just the quantity mu. All right, the mean. That makes sense. And here's what's different. If we actually try to evaluate the variance for the Lorentzian distribution function, we find out it's undefined. Because those tails drop off so much less rapidly in the case of the Lorentzian function that we just cannot get a closed form value for sigma. It's undefined. So rather than have sigma be in the functional form for the Lorentzian function, that's why the gamma is in there. So we measure the gamma, we define it the same way that we did for the Gaussian function. It's the difference between the 2 points on the distribution that have probability equal to 1/2 on either side of the mean. So gamma is the full width at half max, which makes gamma over 2 the half width at half max. And that's pretty much all there is. So if I go back to the previous slide that shows the graph, you'll see that the full width at half max for The Lorentzian function, since its peak is at about 0.27, the full width at half max would be down here somewhere, right about that width there. So the Lorentzian function is very specialized, but is helpful in those cases where we're looking at phenomena with resonant behavior. Hope that helps. Take a look at the book. You'll get more details there, and I will see you in class.